Hello there, owner of a home computer in the 1980s. Looks like you got a lot of stuff for it. A floppy drive, a joystick, and even a computer magazine. But you didn't get any software for your computer. Don't worry, that magazine has some programs in it that you can type in line by line. How exciting! Go pop up some popcorn, get some sodas, and enjoy the next few hours of tedious data entry. Just be careful not to swap two letters somewhere in the middle of the program, or... Type-in programs are long and full of symbols, letters, numbers, and special characters. Entering them isn't software development, it's closer to transcription, since all you're doing is copying data from one source to another. Tools that assist with software development don't make sense here. We need to make transcription safer, especially for these brand new computer users whose enjoyment hinges on having usable, interesting software. My experience with type-in programs comes from Compute's Gazette, and there are two tools, MLX2 and the Automatic Proofreader. It's the latter I'm digging into in this video because it's an interesting hack on the Commodore 64's basic code input system. There are two versions of the software that I know of. The original one performed very basic checksums, math problems done on blocks of data that can be used to ensure the data was transmitted correctly. These basic checksums helped, but they were incomplete in some key areas. The second version is the one I'm looking into. There's a great description of this new proofreader in the issue it was introduced, but this is Hackerbun, so we're going to dig into the decompiled code ourselves and figure out what's going on. For this, I wrote a small Ruby script to turn the data statements into a binary I'll decompile with Radare2 and DA65. The three improvements over the original proofreader this code considers important are having the correct line number, getting the correct count and position of significant characters, and knowing whether we're in a quoted string or not. When you run the automatic proofreader, it shoves this machine language code we're looking at now into the base of BASIC RAM. Then it changes the start address for new BASIC code to be 256 bytes higher than normal, protecting the proofreader from being overwritten. Then, it replaces a vector, an address to some other code to run, with a pointer to the start of our machine language code. Every time you hit enter after typing a line of code, that vector is looked up and the 6502's program counter jumps to what's inside and starts running the code there. Now it's the proofreader's time to shine. At the start of every line in C64 BASIC is a line number. We take that line number as the base for our checksum calculation. Line numbers go up to 65,536, which is 2 bytes of data. We'll store those 2 bytes in two variables. Let's call them the sum and the overflow. We're also going to keep track of how many significant characters we've seen, characters that count for the calculation of the checksum, and we'll keep track of whether or not we've seen a quote character. Then we'll go through the input buffer, that line of code we just typed in, character by character. If the character we find is a null, we stop and print out the current checksum. Otherwise, we check if the character is a quote character. Unlike modern languages where you can potentially see a quote character in a string due to escaping, the only way we can print a quote in BASIC is with char 13. So if we run into a quote, we always flip the quote switch. Now we need to see if the character we're looking at is significant. There's two cases where it is. It's not a space, or it's a space and the quote switch is on. Because of the way BASIC code is translated into more compact code for execution later, you can type big ol' run-on sentences like this one, and it's the same result as this easy-to-read code below it. Spaces only count if we're in quotes. If a character is significant, we add it to the checksum. We take the Petsky value of that character and add it to the sum. If the result of this goes over 255, the value wraps around from 0 and, in the 6502, the carry flag is set. If that carry flag gets set, we increment the overflow. If overflow overflows, we don't care. It will wrap around to 0 and start again. We do this as many times as the number of significant characters we've seen so far. This means the first character is processed once, the second twice, and so on. This is how we catch transposition errors. For example, dog37 and dog73 will give the same value if we just add up the Petsky values of these strings, but it will have wildly different values if we iterate over each character a number of times, depending upon where that character is in the line. Once we've seen a null and reached the end of the line, we print the checksum. We mash together the sum and overflow parts with an exclusive OR, split the result into two 4-bit values, and use those values to select two characters from a list of 16 to print in the top left corner of the screen. The human typing in the program then compares those characters to what they have in the magazine. When they mistype the number of spaces in a string, or reverse the letters in a variable name, or type in the wrong line number, The checksum will let them know they've messed up. Try again, my friend. Finally, once we're done printing the checksum, we jump to the original address that was contained in that vector from earlier, the tokenizer, that prepares code for future execution. Pretty sweet, huh? Oh, and did I mention that the basic code to load the automatic proofreader also performs a checksum on the data statements contained within to make sure you typed in this machine language part correctly? Checksums everywhere. What I like about this code is how it very elegantly catches the major issues most people, regardless of computer skill level, will have when copying a basic program out of a magazine, and it does it with 4 variables. It's also a good tour into how you can patch running code on a system and tweak parts of it to make it do what you want. Hackerbun!